For years, scientists believed that the brain was static, unchanging, and locked, but our understanding has changed drastically to the point where we now see the brain as plastic and constantly changing. But what if I told you that simply thinking could affect not only the way your brain works, but its physical shape and structure as well? It turns out this is exactly what happens. From a neuroscientific standpoint, imagining an action and doing it require the same motor and sensory programs in the brain. For example, if you were to close your eyes and imagine the letter B, the primary visual cortex lights up in the same way it does when you look at the letter on the screen. Take a moment and imagine yourself writing out your signature with your dominant hand. Chances are, the amount of time it takes you to simply imagine doing it is similar to how long it actually takes to write it out. Try doing the same thing with your non-dominant hand and it actually takes you longer to write and imagine. How is this relevant? Well, because imagination and action are actually integrated and engage the same neural pathways, practicing one actually influences the other. One fascinating study took two groups and had them practice piano for 2 hours a day, except one group was only allowed to use mental practice. They couldn't touch the piano, but would sit in front of it and imagine practicing. The surprising result? The exact same physical changes took place in the motor cortex of both groups. And after 3 days, their accuracy in playing was the exact same. Beyond 5 days, the physical practice group did begin to excel faster, but the imagination group, when given the chance to practice physically, was able to catch up to their skill level quickly. Perhaps more incredible is an experiment which used imagination in an effort to strengthen muscles. Both groups did the same finger muscle exercises for 4 weeks, though one group simply did it mentally. Those who actually did the physical exercise increased their strength by 30%, while those who imagined doing it increased their muscle strength by 22%. This is because the neurons responsible for the movement instruction were still being used and strengthened, resulting in increased strength when the muscles actually contracted. So, while your thoughts don't have some mystical or magical power, mental practice is an effective way to prepare for a physical skill. Each thought actually changes the structure and function of your brain by affecting the neurons at the microscopic level. Though, as much as we wish you could sit there and become the next Mozart, it won't happen without a lot of hard physical work. But a little imagination never hurts.
Imagine for a second a duck teaching a French class, a ping pong match in orbit around a black hole, a dolphin balancing a pineapple. You probably haven't actually seen any of these things, but you could imagine them instantly. How does your brain produce an image of something you've never seen? That may not seem hard, but that's only because we're so used to doing it. It turns out that this is actually a complex problem that requires sophisticated coordination inside your brain. That's because to create these new, weird images, your brain takes familiar pieces and assembles them in new ways, like a collage made from fragments of photos. The brain has to juggle a sea of thousands of electrical signals, getting them all to their destination at precisely the right time. When you look at an object, thousands of neurons in your posterior cortex fire. These neurons encode various characteristics of the object: spiky, fruit, brown, green, and yellow. This synchronous firing strengthens the connections between that set of neurons, linking them together into what's known as a neuronal ensemble. In this case, the one for pineapple. In neuroscience, this is called the Hebbian principle. Neurons that fire together, wire together. If you try to imagine a pineapple later, the whole ensemble will light up, assembling a complete mental image. Dolphins are encoded by a different neuronal ensemble. In fact, every object that you've seen is encoded by a neuronal ensemble associated with it, the neurons wired together by that synchronized firing. But this principle doesn't explain the infinite number of objects that we can conjure up in our imaginations without ever seeing them. The neuronal ensemble for a dolphin balancing a pineapple doesn't exist. So how come you can imagine it anyway? One hypothesis, called the mental synthesis theory, says that, again, timing is key. If the neuronal ensembles for the dolphin and pineapple are activated at the same time, we can perceive the two separate objects as a single image. But something in your brain has to coordinate that firing. One plausible candidate is the prefrontal cortex, which is involved in all complex cognitive functions. Prefrontal cortex neurons are connected to the posterior cortex by long, spindly cell extensions called neural fibers. The mental synthesis theory proposes that, like a puppeteer pulling the strings, the prefrontal cortex neurons send electrical signals down these neural fibers to multiple ensembles in the posterior cortex. This activates them in unison. If the neuronal ensembles are turned on at the same time, you experience the composite image just as if you'd actually seen it. This conscious, purposeful synchronization of different neuronal ensembles by the prefrontal cortex is called mental synthesis. In order for mental synthesis to work, signals would have to arrive at both neuronal ensembles at the same time. The problem is that some neurons are much farther away from the prefrontal cortex than others. If the signals traveled down both fibers at the same rate, they'd arrive out of sync. You can't change the length of the connections, but your brain, especially as it develops in childhood, does have a way to change the conduction velocity. Neural fibers are wrapped in a fatty substance called myelin. Myelin is an insulator and speeds up the electrical signals zipping down the nerve fiber. Some neural fibers have as many as 100 layers of myelin. Others only have a few. And fibers with thicker layers of myelin can conduct signals 100 times faster or more than those with thinner ones. Some scientists now think that this difference in myelination could be the key to uniform conduction time in the brain, and consequently, to our mental synthesis ability. A lot of this myelination happens in childhood, so from an early age, our vibrant imaginations may have a lot to do with building up brains whose carefully myelinated connections can craft creative symphonies throughout our lives.